So yesterday we have seen about probability distribution and also how to find the probability distribution in n steps. What we will do today is something about stationary distribution. So this is about the prediction that I said from the very beginning of what we will do. Okay, because when you have a Markov chain and suppose that transition matrix is regular, then after infinite steps the probability distribution will stabilize. What I mean, like, it won't change anymore. What really happens if the probability distribution stabilizes? It means that you will have an idea of what the probability is going to be in the long run. As time approaches, the probability distribution stabilizes, so you will know with certainty about the probabilities associated with each state. This will happen only when the transition matrix is regular. Let's add the transition matrix of a Markov chain be regular. What do you mean by regularity? You just need to remember that transition matrices, they are stochastic matrices. So stochastic matrices, they can be regular. So when they are regular, this will happen. If P0, P1, P2, and so on, if these are the probability distribution, then in the long run, that is, as n approaches infinity, the probability distribution stabilizes. Okay, and when it stabilizes, this probability distribution will be called as the stationary distribution. That is, it will no longer change. This probability distribution is called as a stationary distribution. How exactly do we find this stationary distribution? Of course, I mean, like, we can use limits. N tends to infinity. Pn, over here again I repeat, this one is not p power n, it is just a notation for the n step probability distribution. So when limit n tends to infinity, this one, it is the stationary distribution. Okay, so you just need to remember that this one, it will be a vector. Okay, it will be a row or a column vector depending upon the books. Okay, some of them they think of this one as a column vector, some of them think of this one as a row vector. Okay, but we will think of this one as a row vector. Okay, so a probability distribution, it is a row vector. Finding this limit, it will be difficult. Okay, because first of all we just need to find Pn. Okay, and then we can take the limit. It will be too complex. So what will we do? We actually have a theorem. This theorem states that the probability, the stationary distribution of a Markov chain whose transition matrix is regular is the fixed probability vector. That is, limit n tends to infinity, Pn, it is equal to u, where the vector u, this u, this vector, is the fixed probability vector of P. Okay, inside bracket again, u is the fixed probability vector of P. So if you need to find u, you just have to use up equal to. Okay, so with this theorem, let us just try to do some exercises, then you will be more familiar. Okay, so sorry, I mistakenly put some formulas that are not related at all. It is, in fact, okay, it is also a question relating to the things that we had done. Okay, but if you take a look at question 3, okay, question 3, okay, just let me expand it. Question 3, it says, in the long run. In the long run, what is the probability that there are 2 red marbles in urn A? Okay, so whenever you see the question about in the long run or as time approaches, just know that it is a question about stationary distribution. Okay, so let us try this example. Remember that we have to find the transition matrix. If you take a look at question 1, okay, so we will need to find the transition matrix. So let us try to understand the problem. Okay, so over here we are having two urns. Okay, urn A and another vessel B. Okay, so there are 2 white marbles in urn A and 3 red marbles in urn B. So what is happening here? Okay, just let me expand this picture. So you are having these 2 marbles here which are white. Okay, I'm not coloring them, and you are having these marbles over here which are red. Okay, I've painted them black. So what is happening at each step of the process, a marble is selected from each urn and they are interchanged. So I will take 1 marble from here, 1 marble from here, and I will interchange them. Okay, so on interchanging you can have this picture, okay, where we are having 1 white marble here and 1 black marble here, and also in this urn B, after interchanging you will be having 1 white marble and 2 red marbles. Okay, but you can also do this again. Okay, you can interchange 1 from here, 1 from here. You may end up with this stage. Okay, so this is urn A. Okay, if you interchange, you may also have 2 blacks here and 2 whites and 1 red. Okay, so these are the possible states. Okay, if you see, okay, if you interchange from here again, you will reach this. Okay, if you interchange, you will reach this. Okay, also, okay, just take a note. Okay, you can even interchange, okay, because you are not looking when interchanging them, or even if you look, it doesn't matter. You can interchange a white and a white, okay, but you will reach this same state. Okay, so that's why I'm not drawing it. Similarly, you can exchange a black and a black. You will have the same state over here. You can take black marble from here, black marble from here, interchange them. You will be having the same state. That is why I'm not drawing it anymore. So we had seen that these are the possible states of the system. We need to find the transition matrix. The transition matrix, if you remember, it is involved with 2 states, the preceding state and the succeeding state. So over here we can have the preceding state to be A1 and the succeeding state, it can be A1. Okay, is it possible or not? Is it possible or not for the preceding state to be A1 and then from A1 it will change into A1 again by interchanging? Is it possible by interchanging 1 marble from here and 1 marble from here? Is it possible to reach the state A1 again? It is impossible, right? Impossible. So that is why the transition probability P11, the probability on changing from A1 to A1, it will be equal to 0. Now let us have the preceding state to be A1 and the succeeding state to be A2. Is it possible or not? Is it possible or not to have the preceding state to be A1 and the succeeding state to be A2? Yes, it is possible by interchanging. Okay, so this one is possible. How is it possible? Let us see. 1, 2. Probability that the state changes from A1 to A2, it's equal to probability of taking, we need to take 1 white from A and 1 red from B. 1 white from A and 1 red from B. How much is the probability of taking a white marble from A? It's equal to 1. Okay, because there are only white marbles. Okay, so the probability of choosing a white marble from A, it's equal to 1. We are having the word and, so multiplication. Okay, probability of taking 1 red from B. There are only red marbles here. Okay, so the probability of choosing a red marble, it will be equal to 1 because it is guaranteed that you will be getting a red marble. So P12, it will be equal to 1. Again, we are having 1 because it is guaranteed that we are having white marble, and it's related to multiplication when the events are exclusive. Okay, what I mean is the outcome of the event from here is independent. It does not depend on the outcome of the event from here. Okay, the event of choosing a marble from here does not depend on the outcome of the event on choosing. Okay, so they are exclusive. That is why it will be multiplication. Okay, so it will be 1. Okay, so let us just keep track of these probabilities. We are having P11 it's equal to 0. P12 it is equal to 1. Okay, now let us just see from E1 to E3. By interchanging, is it possible for the state to change from A1 to A3 by interchanging one marble? Okay, it is impossible. Hence, P13 it will be equal to 0. Okay, I'm just writing it here. P13 will be equal to 0. Okay, I like to keep track of these probabilities because I know that their sum should be equal to 1. So over here the sum is equal to 1. It's alright. Okay, so we have done all the preceding states with A1. Now we can change the preceding state to A2. A2, can it change to A1? We will see. From A2, can it change to A1 by interchanging? Yes, it is possible. We can do this by taking the red from here, put it over there, and taking the white from here, put it over here. Then it will change to state A1. Okay, it is possible. P21. Probability that the state changes from A2 to A1, it's equal to, okay, it's equal to probability of choosing. We need to take the red from A, one red from A, and one white from B. Okay, and then we can interchange them. Okay, so what is probability of taking one red from A? 1. How many marbles over here? There are 2. Okay, in 2. Again, we are having an independent, exclusive events or independent events from B. Okay, so we are having 1. So how many marbles are here? There are 3. Okay, so the total probability will be 1 by 6. So P21 it will be equal to 1 by 6. Okay, let me just write it here. P21 equal 1 by 6. So this is the probability that the state changes from A2 to A1. Now let us see from A2 to A2 whether it's possible or not. Okay, from A2 now we will see whether it can change to A2 or not. Okay, is it possible or not that the state changes from A2 to A2 by interchanging? It is possible. We can take the white from here and the white from here, interchange them. Or we can take the red from here and the red from here and interchange them. Okay, so over here this P red. P22, it's equal to probability of choosing one white from A and one white from B. Okay, so we can take the white and the white interchange them, or we can take the red and the red interchange them. It will be the same thing. We will be reaching from state A2 to A2. So that's why I will write over here or. Probability of choosing one red from A and one red from B. So how much is this equal? What is the probability of taking one white from A? 1 out of 2 times, this is n, one white from B, this 1 by 3, plus one red from A. One red from A, this 1 by 2. There is one red ball, total it's 2, and one red from B. So it will be 1 out of 3 again. 2 out of 3, because there are 2 red. There are 2 red over here. So possible divided by total. So it will be this. Okay, so this one will be 1 by 6 plus 1 by 3. Okay, we can take the LCM. 1 plus 2, so it will be 1 by 2. So P22, it will be equal to 1 by 2. Okay, so this is about P21, P22. Now we can just find P23. Okay, P23. Okay, preceding state is A2, succeeding state is A3. So we can find P23 will be equal to 1 minus P21 minus P22. So it will be 1 minus 1 by 6 minus 1 by 2. 6 minus 1 minus 3, 1 by 3. Okay, so it will be equal to 1 by 3. Okay, so P23 will be equal to 1 by 3. Okay, similarly we can have the preceding state as A3, succeeding state as A1. Can it change from state A3 to A1 by interchanging the marbles? It is impossible. So that is why it will be equal to 0. P31, it will be equal to 0. What about A3 and then A2? Is it possible for the state to change from A3 to A2? It is possible. How will we do it? We can take one red from A, P2, it will be equal to probability taking one red from A and okay, we can take white from B, okay, and then interchange them. Then we will convert it from stage 3 to stage 2 and one white from B. So probability of choosing one red from A will be equal to 1 because it is guaranteed that you will be getting a red, times one white from B, one white, so it will be total possibilities of white balls, it is 2 divided by the total number, which is 3, so it will be 2 by 3. Okay, so okay, now I don't need these anymore. Okay, I hope it is clear how we are calculating these probabilities. So P31 it will be equal to 0, P32 equal to 2 by 3. Now we just need to find P. Okay, so preceding state is A3, succeeding state is A3. So transition probability will be P33, it will be 1 minus P31 minus P32. 1 minus 0 minus 2 by 3 will be equal to 1 by 3. Okay, so P33 it will be equal to 1 by 3. Okay, so we have done all the possibilities. That is why now we can just write the transition matrix. Therefore, the transition matrix is P. A1, A2, A3, these are the states. Again, you don't need to write them. A1, A2, A3. P11 it is 0, P12 it is 1, P13 it's 0, 1 by 6, 1 by 2, 1 by 3, 0, 2 by 3, 1 by 3. Okay, so this is the transition matrix. Okay, and if you notice, it is indeed a stochastic matrix, because if you add the rows, it will be equal to 1. Okay, so that was the transition matrix. Now let us see the next part of the question. Okay, so first question is done. What is the probability that there are, question 2, 2 red marbles in urn A after 3 steps? Probability that there are 2 marbles in urn A after 3 steps. Okay, so again, it doesn't state anything about the change, so we will first need to find the probability distribution in 3 steps. For this, okay, the initial probability distribution is, okay, how did I get this one? Because initially the system was in state A1. Okay, so this is the probability that the system is in state A1. This is the probability that the system is in state A2, and this one is the probability that the system is in state A3. If you take a look at the first line in the question, you are seeing that there are 2 white marbles in urn A and 3 red marbles in urn B. That is why over here it's guaranteed that the system is in state A1. P1 will be equal to P0P, which is 1 0 0, times the transition matrix. The transition matrix was 1 0 1 0, 1 by 6, 1 by 2, 1 by 3, 0, 2 by 3, and 1 by 3. So multiply them, you will be having P1. Okay, so P1 will be 1, sorry, will be 0, 1, and 0. Okay, so this is P1. Now let us calculate P2. Okay, the probability distribution in 2 steps. P2 will be P1 P, which is equal to 0 1 0, again times that matrix 0 1 0, 1 by 6, 1 by 2, 1 by 3, 0, 2 by 3, 1 by 3. Okay, we can calculate, multiply them as matrices. Multiply them as matrices, you will be having 1 by 6, 1 by 2, 1 by 3. So this is the probability distribution after 2 steps. We need the probability distribution after 3 steps. Okay, we need the probability distribution after 3 steps. So P3, we can calculate P3. Okay, we can calculate P3 will be equal to P2P. So P2 is equal to 1 by 6, 1 by 2, 1 by 3, times this matrix, capital P, 0 1 0, 1 by 6, 1 by 2, 1 by 3, 0, 2 by 3, 1 by 3. Okay, so we just need to multiply them. It will be 1 by 12, 1 by 6 plus 1 by 4 plus 2 by 3. Okay, and then 1 by 6, 1 by 6 plus 1 by 9. Okay, so just add them, you will be having 1 by 12. Okay, will be 12, okay, 2 plus 3 plus 4, 8. Over here will be 18, 3 plus 2. I hope I did not make any mistake. 9, 10, 13 by 12, 5 by 18. So sorry, okay, 4, 4, 3, 3, 4, 4 to 8, 10, 11, 12, 13. So this one will be equal to, this one will be the probability distribution. Okay, so the question asks, what is the probability that there are 2 red marbles in urn A after 3 steps? Probability. Okay, so we need to find, okay, if you take a look, after calculating all this, we need to find the probability that are 2 red marbles in urn A after 3 steps. Okay, so there are 2 red marbles when it is in state A3. Okay, if you notice what I had drawn before, there are 2 red marbles in state 3. Okay, in state 3. Okay, so this question, it is related to state 3. Okay, since it's related to state 3, this one is the probability attached with the first state, probability attached with the second state, and probability attached with the third state. So that's why it will be 5 by 18. So we are done with question 2. Now let us try question 3. In the long run, what is the probability that there are 2 red marbles in urn A? Again, it is associated with state 3. So let us find the stationary distribution. We are finding the stationary distribution because it is the question asks you in the long run. Be the fixed probability. We are finding the fixed probability vector because the fixed probability vector is related to the stationary distribution. Let U be the fixed probability vector of A of the matrix P. So what can we have? So UP, it will be equal to U. You can write it as U1, U2 and U3, but because it is a probability vector, so you can write 1 minus U1 minus U2 times the matrix P. The matrix P, it was 1 0 1 0. Okay, just let me check. The matrix P, it was 0 1 0, 1 by 6, 1 by 2, 1 by 3, 0, 2 by 3, 1 by 3. So it will be equal to U, which is U1, U2, 1 minus U1 minus U2. So we can multiply this one and this. We will be having U2 by 6. And over here, if you multiply U1, you will get U1 plus U2 by 2 plus 2 minus 2U1 minus 2U2 upon 3. And this one you will be getting U1 times 0 will give you 0, U2 by 3 plus 1 minus U1 minus U2 upon 3. It will be equal to U1, U2, 1 minus U1 minus U2. So now what we can do, we can equate them. Okay, we can equate. So the first one will give you U2 by 6. U2 by 6 equal U1, the first coordinate, or the first entry of the matrix. And over here, the second entry is U1 plus U2 by 2 plus 2 minus 2U1 minus 2U2 upon 3. It will be equal to U2. We actually need only two equations because we are having only two variables, U1 and U2. Okay, we don't need this third coordinate. Okay, only if you don't have only if you cannot solve from the two of them, then you will be needing the third entry as well. Okay, so over here we'll be having U2 equals 6U1, and over here, okay, substituting U2 equals 6U1 over here, we'll be having U1, U2 it is 6U1 plus 2 minus 2U1, U2 it is again 6U1, so we'll be having minus 12U1 on 3. And U2 is 6U1. Is U1 plus 3U1 plus 2 minus 14. 14U1 on 3 equals 6U1. Now just define U1. This U1 plus 3 will be 3 minus 14U1 on 3. 6 minus 4 will be 2U1. 2 minus 14U1 will be equal to 6U1. So U1 will be equal to 1 by 10. Therefore, U2 it will be 6U1, it will be 6 by 10. And we can find out U3, and U3 will be 1 minus U1 minus U2, the third coordinate. So it will be 1 minus 1 by 10 minus 6 by 10. 10 minus 7, it will be 3 by 10. Hence, U, the fixed probability vector U, it is equal to U1, U1 which is 1 by 10, U2 it is 6 by 10, and U3 it is 3 by 10. But if you remember, we need to find, if you take a look at the question, in the long run, what is the probability vector that there are 3 red marbles in urn A? Okay, so I will write it down. There are 3 red marbles in urn A. In urn A, if the system is in state A3. Okay, so if the system is in state A3, then there will be 2 red marbles. Okay. 2 red marbles in urn A. This one is related with state A1, this one is related with state A2, this one is related to state A3, hence, okay, required probability, it's equal to 3 by 10, okay, which is this one is related to the state A3. So I hope that is clear. Until next time.